Weather is like politics and real estate. Local really matters.
And what happens to you where you live is very important. Most of us who live in the southeast and in North Carolina are very familiar with summertime storms where it may rain like crazy, thunder and lightning in your neighborhood. You drive a few miles away, go to the mall and shop, and it hasn't even rained at all. Wintertime, very similar type conditions, heavy snow and sleet in conditions in one part of the county, perhaps other parts of the area, much different conditions. So local matters.
And it matters even more when it comes to lightning.
That's largely a result of the number of storms we get and also an impact because of lifestyle, sociological issues. Lots of people at the beach, lots of people playing golf, lots of folks still on the farm and doing things outside, and that's a threat that we take very seriously.
So this shows, again, high-speed photography.
Which is why Gary Lackman from North Carolina State University's Department of Marine, Earth, and Atmospheric Sciences is working with the National Weather Service to improve the understanding and forecasting of lightning.
The summer air mass here is hot and humid and unstable. And we also, along the coast, you have the sea breeze that helps to lift the air and release that instability. So all the ingredients are there, and you have something to light it off. You know, you have the fuel and you also have the spark.
But first, a quick lesson about why lightning, well, lights up. To begin, you need ice. That's right, ice. So you need a cloud that is sufficiently tall enough to reach colder air temperatures, so there will be ice. All those ice particles swirling around in the cloud bang into each other. That causes a separation of charged particles. Positively charged particles rise to the top of the thunderstorm. Negatively charged particles and hailstones drop to the bottom of the cloud. As the charge grows, the negatively charged bottom of the cloud sends out an invisible channel towards the ground. As the channel gets close to the ground, positively charged objects on the ground attract it. The channel develops, and the electrical transfer in the channel is lightning.
The thing that people don't understand about lightning is that it comes in different flavors. You can have a positive or a negative lightning discharge. You can have cloud to cloud, within cloud, cloud to ground, cloud to air.
Lightning-related fatalities have dropped thanks to technology showing the current location of storms. Meteorologists can also predict the odds of a storm forming in a given area. The goal for weather researchers is precision forecasting, predicting when and where a storm will hit.
You basically have all the equations that govern the motions of the atmosphere, and you program them in, and you can integrate them forward in time. And if you have instability, and you have moisture, and you have some kind of a triggering mechanism, then you know you have the ingredients for lightning, for thunderstorms. And we can predict those things pretty well. You know, you can predict the environment of the storm pretty well. What's harder is to say, okay, there will be a storm over Chapel Hill, North Carolina at 3:53 p.m. on Saturday. You know, we don't have that kind of precision.
Well, the storm has passed. You might be able to see that the parking lot is still wet, and North Carolina certainly has its share of storms. The most are in the summertime. It's probably no surprise because that's when the atmosphere is the most unstable. But nothing compares to central North Carolina on July 28, 2005.
There were 39,754 cloud-to-ground strikes observed within this 24-hour period.
That was the worst day ever for lightning strikes in the state.
Since we know the ingredients of lightning, we can predict the lightning strikes, the general area of where these strikes are going to be, and the number of lightning strikes in that area. So what I was doing was I was testing different forecasting equations that are available in the model and trying to compare those to the actual observations.
So I think now you're starting to blend the computer models with the radar to say, okay, we can project and make sort of a short-term forecast of where the lightning will be a couple of hours from now. What you'll see in the next 5 or 10 years is the ability to say, okay, you have a football game at the stadium. 2 hours from now, there will be storms over the stadium at that time, and you should delay the start of the game.